Hi everyone. In this tutorial, you will learn how to perform channel sounder sample experiment in AERPAW development environment. We'll follow the instructions in this page in the user manual to perform the experiment, and later we'll use the second page here, channel sounder post-processing, to process the results that you obtain by performing the experiment. So this experiment assumes you first go through the web portal, and then you create an experiment. You initiate in the development mode. You create experiment and initiate in the development mode. And the experiment that you create should have one fixed node, which is LW1, and the portable node. Fixed node will be used as the transmitter, and the portable node will have a channel sounder receiver in the portable node, as well as a vehicle application that will use the default plan. And then we'll measure the signal strength while the portable node follows the default plan. So when you initiate development, you will have two files, the manifest and the OVPN profile, and then you need to download them in your computer. So which are downloaded in here. This is the manifest, and this is the profile. And in my case, I am using a Windows device, and I'm using OpenVPN. So for Windows, you download the OpenVPN from the OpenVPN webpage, and then you go in the system tray, and then you right-click, and then you first import the profile using import file here, and then it will appear in here, and then you connect to the profile. Right now, I am connected to the profile of the experiment. So when that happens, if you go to command prompt or in the terminal, if you are using Linux or Ubuntu or macOS, if you type ipconfig or AERPAW, you will see there is an interface which is 192.168.137.52. The last two digits may be different, but these should match the IP addresses in your manifest. For instance, in my case, the manifest IP address is 192.168.137.1, which is the first node. .2 is the second node, and .62 is the OEO console. Once you have connection to the experiment network, you need to SSH into the experiment. In my case, I am using a mobile external, which I download from this link here, and then I launch it. And then, as you see, I pre-configured my mobile external with the EVM, M1, EVM, M2, and the OEO console. You can do that by clicking on this session and then clicking on SSH. And then if I check the properties of this connection, what you need to do is in these remote hosts, you need to provide root at the IP address. And it's very important that you also provide your private key that you provided to AERPAW portal. And then you can leave everything else in the default configuration. So if I double click here, then I have the SSH into the first node in my experiment. And if I go back here, I can open another window another terminal window to connect to the second node, which is the fixed node. And then, although it is not necessary for this experiment, you can also SSH into the OEO console. So now we'll follow the instructions in the user manual to configure the radio aspects of the experiment. And then we'll also go through, first we will do the experiment without any vehicles, and then we'll repeat it with vehicles. So performing experiment, what you need to do, first we'll configure the transmitter. So let's copy this here. Okay, so this is the folder that contains all the sample experiments in AERPAW platform. And one of them is the channel sounder. So if I go back to here, you see the first node is the node number 1 is the portable node, and node number 2 is the fixed node. So transmitter, I will implement in the fixed node. So I need to go to second EVM M2. And then I do shift insert to paste the command I copied from the user manual. So in this folder, if I do ls, you will see there are two folders. One is helpers and one is the samples. So if you go to the samples folder, and then if you do ls, so you will see all the samples in the AERPAW platform, and one of them is the channel sounder here, receiver and transmitter. For this case, we are using we are gonna implement the transmitter code. So I go back to the radio. So the next command assumes I am in the radio folder. So if I go back to the menu, I am in the radio folder, and then I copy this code. So what this code does is it copies the channel sounder tx script as the startradio.sh script. If I do ls, you see the startradio.sh is in here. So this code, so the startradio.sh is already in the start-experiment.sh script, which is under root, but it is commented out. If I want to implement a radio application in this node, I need to uncomment that line. So so it's also explained in here. So we need to edit this root start experiment.sh script, and then we need to uncomment the radio start radio.sh. So radio start radio.sh. So this file is actually pointing to this file. So, and then we copy this file from the channel sounder tx script. So I go to the root folder, and then I do nano start experiment.sh. So you can use any your favorite editor in here. So here you see there is this radio start radio.sh script, but it is commented out. So I uncomment it, and then I click Ctrl X, and then it asks me to save the modified buffer, and I click here Y, and then enter. So now the start experiment script has been edited. So now I will do the same thing in the for the receiver, which is the EVM M1, I copy. So the first is the same for both cases. I copy the paste it in here. So I'm in the radio folder. So now instead of the TX, in this case I will copy the RX. I do shift insert. Now if I do ls, you will see there is the start radio.sh, which is copied from the channel sounder receiver script. I go back to the root folder by CD, and then I do again nano start experiment.sh, and then I need to uncomment this first line to uncomment the start radio.sh script. So although in both M1 and M2 we uncomment radio start radio.sh script, but in the first one is copied from the receiver script. In the second one, it is copied from the transmitter script. And this is the way we follow for all the sample experiments. So now we are, so the configuration for the transmitter and the receiver is complete. But before you start any experiment, it is advised that you perform reset in one of the EVMs. So you can do it either from the first node or you can do it from the second node. So it shouldn't matter. So what this reset does is it goes through the CVMs that control the vehicle and also the CAN VM. It resets it to a working state. So in this case, so this first node is a portable node. In the portable node, you will see screens such as OEO agent, filter, mount proxy, CTL, and remote server. And in the, so this is the CVM for the fixed node. You will see here OEO agent and remote server. So this mount proxy, filter, and CTL is for the portable node. So you don't have them in the fixed node. And the last one is the channel emulator VM. Now we are ready to start experiment. So in order to start experiment, what we do is I will first go to the transmitter and then type start experiment.sh. So what this will do is it will start the processes in the background in a screen terminal. So to see which terminals are running, you can type screen -ls. And the screen -ls shows there is the transmitter GNU radio flow graph is running. You can go inside by typing screen -r and then name of the screen, which is TX GRC, and enter. So when you press enter, it will go to the screen that runs the transmitter GNU radio flow graph. So in this terminal, if you want to go back, so you may want to go here to see if there are any warning or error messages. Other than that, transmitter is just transmitting a pseudo-random sequence in a GNU radio flow graph in a continuous manner. So in order to exit from the screen, what you need to do is Control-A and then followed by Control-D. So this will put you back into the main terminal of the second portable node. So now we have started the transmitter, and let's go back to the first node and then start the receiver. So we start the receiver similarly by typing start experiment.sh. when we do this, so if you type screen minus ls, so in this case, it has 3 terminals. If you go to the receiver GNU radio screen, you can do it by screen minus r, rx, grc. So this is the so it runs, and if you see any if you don't see any warning messages, that's good. So you can go back by typing Control A, Control D, and then let's look at the other terminals. Remember, we had the power and quality. If you go to screen minus R, power, so you see, so these are the received signal strength, which is around 43 in this case. Is printing on the screen with a timestamp. So the second column is the address. It increases. So we can go back by Control A, Control D, and then we can go back to the other terminal, which is quality. So the quality, we use it to see if the signal measurement is valid or not. If the quality is above 70, which means the received signal, received power measurement is valid. So we'll use this in the post-processing code that we'll later see. So I click Control A, Control D to go back to the main terminal. So as you see, for when we only have when we don't have the vehicle application, then if you don't run any vehicle application, that means portable node is in a fixed position, and our default position is maybe around 20 meters away from the Lake Wheeler 1 fixed node. So we see in this case the power and quality doesn't change much. So now that we saw how the radio works, the channel sounder works, we can also add a vehicle. But before we do that, we need to stop this experiment by typing stop experiment.sh in the root folder. So I first stop the receiver, and I need to do this for the transmitter as well. And then, as I mentioned, it's always good to reset after each experiment or before we stop an experiment. So what happens when you run an experiment, right? After experiment finishes. So we log everything in folder called results under root. If you go to the results folder and if you do ls, you see, so the screen that run the transmitter flow graph has generated this log file. There's only one log file for the transmitter when we have a channel sounder. So if I print the contents of this file, you see it's the same as what we saw when we went inside the screen of the transmitter. So in here, the reset finished. We can also check what happens in the results folder of the portable node. And I go inside the results folder and then I do ls. Delete media minus AMP. And then you see in this case, there are 3 logs. Power, quality, and the receiver flow graph logs. So the post-processing code that we provide is when we include the vehicle in the experiment. So let's also do that. So when we add vehicle, we don't need to change the transmitter. Transmitter will be the same, but in the portable node, we will add the vehicle application. And how do we do that? We do that by going to this section 3 of the user manual, and then 3.4, where it explains running sample experiment software. You see here, it talks about how in AERPAW sample experiments have 3 different scripts. One is for radio, one is for vehicle, and one is for traffic. For the channel sounder, there is no traffic, but we have other sample experiments that also you can run traffic on top of the radio. So we go down here, and then you see there's a section for setting up the vehicle script. So this is similar to the setting up the radio script, where instead of going to the radio folder under profile scripts, in this case, we go to the vehicle folder. So I copy this here, and then I go to the first node, EVM M1, and then I paste it here. Okay. So now I'm in the vehicles folder, and if I do ls here, you see there are 2 folders similar to radio, and then inside the samples, so we have again sample applications for the vehicle. So I go back to the vehicle folder, and then I go back to the user manual and copy. So this is the default. So this is, we will use the start pre-plan trajectory script, which uses a default plan. We'll see later. Okay, I pasted here. Now I do have the start vehicle.sh script under vehicle folder. Now I need to go back to the root folder, and then I edit the start experiment.sh script, and then I need to uncomment this last line, so that it will run both the radio script and the vehicle script. So now, so far we have run the channel sounder experiment without vehicle. We started experiments on both EVMs, and then we stopped them, and then we reset the CVMs and the channel emulator VM. Now we added in the portable node a vehicle application as well. So we will start experiments similar to the previous one, but because we do have a vehicle application in the portable node, we would like to set up the Q ground control, and we'll use the Q ground control to arm our vehicle after we start the experiment. And also we can use Q ground control to visualize the when our UAV carrying the portable node is moving. So to do that, first I need to set up port forwarding. So for this case, I already done port forwarding, but you can do by going to the manual, search for port, and then I think it's the first one, local port forwarding. It explains how you can do it for different platforms. For my case, I will be using the Windows and mobile external. So what I need to do, okay, let me go back to mobile external. And then in tools, there is this port forwarding menu item here. You see, I already configured it. So you if you have not done that, you can click on this need SSH tunnel. And then if you click edit, so it will take you to a screen like this. So what you need to do is, so if your portable node is the first node, then this is going to be this port will be 5761, and 1 is the node number. So if it is node number 2, it should be 5762, and so on. So this is the local IP address. So this one you need to change this IP address with the IP address of your OEO console, which in my case, in the if you check the manifest, you will see is this is the IP address. So this IP address comes from your manifest. And then this 22 is the for the SSH. And similarly here you put 5761, which is the same as this one. So once you do this, you go here, and then you need to provide your private key to the port forwarding configuration as well. And then once everything is done, you can give it a name, let's say Q ground control, and then you click on start. So when you click on start, so you will see the play button goes, the play button goes disabled, and then the stop button becomes enabled. So you can stop it anytime you want. And make sure, like when you click this button, if you don't choose any file, it will go like this, and then it's not going to connect. So I go back here, I click this one, and then click open. Okay, so you need to be careful about this. Now I minimize this window. So now we are we configured our mobile external for port forwarding. Next step is you so this assumes you already downloaded and installed Q ground control. This is the link for the Windows, and you can also do it for other platforms. So now I launch Q ground control. So the first thing that you do when you launch Q ground control is you click on here, and then you click on application settings, and then communication links. So you need to, if you don't, I already configured it, but if you did not do that, you need to click add, and then you will have like a screen like this. You can give it a name, type TCP, server address is local IP address, and then port number is the same as you used in the port forwarding. And then you click OK, and then you click connect.
Stabilized flight mode.
So you will see stabilized flight mode. You click on OK here, and then you click on back. Then you see this arrow that shows the location of the UAV in the default position. So it says here ready to fly. So now we can go back to experiment and start it, and then we'll arm it from here. So now I go back to the root folder in the transmitter, and then I click on start experiment.sh. So before I do that, so let me do screen -ls. So you need to make sure there are no screens running in the background before you start an experiment. And then you do start experiment.sh. And then if you do screen -ls, you will see the screen corresponding to the transmitter GNU Radio Company logo. And here we do the same. Let's first check screen -ls, and then there are no screens running. So we do start experiment.sh, and then if we do screen -ls, it will show So we used to have power, quality, and RxGRC screens before. Now we also have the vehicle screen. If you check screen minus R vehicle, so you should see that waiting for safety pilot to arm. Okay. So this is what you should see. So right now the vehicle is waiting to be armed, and then you can arm it using. You can either do it from the OEO console. Like if you do screen minus ls, you should see a screen on my proxy. You can go inside this screen and then you type arm throttle. Another way is if you watch the tutorial, the other tutorial, you see there is start OEO console.sh. You can run this script and then you can arm it using the console script. But in our case, what I will do is I will go to the Q ground control. I click here, and then I click arm, and then select here.
Arm.
So now you see
Flight mode.
it says in this terminal taking off. So it's going to 25 meters. So you see like the height is increasing here. And once it reaches the 25 meters, it will go to first waypoint and then second waypoint and so on until it comes back and then lands. Okay. So we are in the screen terminal here, vehicle screen terminal. Now let's click on Control A, Control D, and then let's go to the power screen. So remember the power in the default position was 43, but as you see, while the UAV is, so here is the transmitter is around here. While the UAV is moving away from the transmitter, the signal strength,
Communication loss.
you see the
Communication
signal
is low.
strength is reducing. Okay, so we wait for the vehicle to land. So you see now it started increasing again because it's coming closer and closer to the transmitter.
Communication loss.
So let me,
Communication regained.
so this is the
Flight mode.
power screen. Let me go back to the main terminal by clicking Control A, Control D. And if I do screen minus ls again, you see all the screens here remaining. But when the vehicle lands, after some time, the vehicle screen will terminate. At that point, we can stop experiment.
Disarm.
Let me go back to the vehicle screen. You see, it says there is no screen to be resumed, matching vehicle. If I do screen minus ls, you see the vehicle screen stopped. At this point, you can stop the experiment. So I will first stop the receiver, and then I go here and then I stop the transmitter. Now, if I go to the results folder again, you will see there are two log files corresponding to the experiment with without vehicle and experiment the with vehicle. And then, so they are timestamped. So if I do the same in here, so we will have the logs corresponding to, so these 4 logs are correspond to the experiment without vehicles, and these 4 actually I think these 3 plus so that these 3 correspond to the logs corresponding to without vehicle, and these 5 correspond to logs with vehicle. So when you have vehicle, you see we have these 2 extra log files. So we'll see their contents in a bit. So now we collected the we performed the experiments. We collected the log files. We'll see now how we post-process them. Okay, so if you go back to our user manual, sample experiments, radio software, junior radio experiments, channel sounder. So we performed the experiment in the default configuration. So I can close this one. So we perform the experiment in its default configuration. And if you want to modify parameters, you can also do that by following, so by editing this file. So such as you can change the frequency of if you want to transfer a different frequency than the default one. That's the file that you need to edit, and also you need to edit the receiver, and then so we have the results in the results folder. So we have the second page here to go through how you post-process the log files. So in order to do that, we first need to download the code in this link. I would suggest you right-click here and then you open the link in incognito window, and then you click on download all. Okay, if when you do that, you will see the code downloads like this. Okay, it takes some time, so this is the what you should see after the download finishes. So the post-processing will do it in MATLAB. So what I will do is I will first show the sample experiment that was performed earlier, and then we'll repeat the same processing for the experiment that we just did. Okay, so I go here and I double click here, and then I paste it. So there is a folder which contains some files. So I copy the entire folder under this MATLAB directory. Okay, and then I go to if you go to MATLAB, if you launch MATLAB, so this is the file. I mean the zip file that's downloaded. So I double click on the main script. So if you don't change anything here, as you see, if I go back to MATLAB, so here you see there's a logs file, and then I have the logs from an experiment that has been performed before, and then so the code should run without any modifications. So if I click on run here, So this should run without any modification. So I pause the video here and then I will come back when the code finishes. Okay, after a few minutes, the code finishes execution, and then it does two things. It generates some plots, and it also generates this input.csv file that we later use. So the plots are so this is as a function of time, the altitude of the UAV given by the GPS points. The same altitude given by the measurement points. And this is the power as a function of distance. As you see, as the distance increases, the power, as the distance increases, the power decreases. And so this one is show the distance as a function of time. As you see, it starts around 25 meters, it goes up to 215 meters, and then comes back, and then it lands. And then the other plot shows the power as a function of time. As you see, when the distance is smaller, the power is higher. And when the distance is larger, the power is smaller. And finally, we have the scatter plot. So so this is actually a three-dimensional plot, but it shows in 2 dimensions when it first plots. So you need to click this button here, and then you rotate it to see the 3-dimensional view. So as you see, the UAV starts on the ground, it goes up, comes back, and then lands. And so this point here shows the location of the transmitter. So now, so let me close this. Also, let me go back to, so this was the original file, original structure of the files. And this is what it looks like after the code runs. You see, it also generates this input.csv file. But this is for the logs already there. So you can delete this file because we also will create it using the logs from the experiment that we just performed. So if you see in the MATLAB main file, so here you see the 3 logs: vehicle out, power, and quality. So we need to replace these logs with the logs that we just created. But to do that, we need to copy those log files from the from our EVM1 and EVM2 to my local computer. So how do we do that? So if you are using Mobile Xterm, it's very easy. So this is EVM1. You will see here another window which shows the files in our portable mode, right? And here you see like there is the results folder. If I double click here, and then if I make this larger, you see here the logs that we collected, right? So what I can do is I can make this smaller, and then I can open this here. So this is the file we downloaded. So the files we downloaded from post-processing web page. So if what I can do is I can select this, and then I can drag and drop. So this will copy these files into here. Okay, so so I will delete these files from before. So these are the all the log files we have. So you can also do similar with two here. You will see there is it also has the results folder and the two log files in here. So I can also copy them into here. Okay, now so let's see what these files contain. So in this one, it's not it doesn't have much useful information, but if there is anything, any warning or error messages, it should show here. So this one and this one are similar to each other. So actually, I don't need these files, so I delete them. So similarly, so this is the receiver log graph, GRC file. So these also we don't use in the post-processing, so we can delete them. So now we left with these log files. So I want to only use the post-process the log files when there is vehicle. So you see here, I have two of them. One of them corresponds without vehicle and one corresponds with vehicle. And the one that corresponds without vehicle is this one because it's generated earlier. So this 948, this is 1003, 1003. So let's check. So if you check here, you see it's 43, 43 all the way down. 43 is not very interesting. So this one and this one, so I don't need this one as well, so I delete them. Okay, and then for the remaining ones, so we already know what power and quality contain. So we also have these two vehicle logs. So let's first look at this one. So this just shows this vehicle screen. It takes off to 25 meters, it follows the waypoints, and then it's done. So this is also not used in our post-processing, so I can delete that one as well. So the only remaining thing is I need to copy this timestamp because that only the timestamp will be different. I copy it from one of the logs. So all the timestamps are the same for the receiver. I go back to the main script here, and then these timestamps, I replace it with the new timestamp. And then I click on run. So when the code finishes execution, you have similar plots as we saw in the example log files in the Google Drive. So you can do this, right? So this is the distance versus time and power versus time. So this is power versus distance. So these are so we have these two plots. One comes from GPS and one comes from measurement. So what is the difference? So let me briefly explain. So we have two processing functions here. One process to process the GPS, which is the vehicle log, which is vehicle out log. And the other, there's another function to process the measurement, power and quality. So for the GPS, if you look at the GPS log, it contains so this is the vehicle out log file. As you see, it contains here the timestamp. And then, so this is the timestamp, and then we have one GPS point every 1 second. So this is 19, 20, 21, 22. Every 1 second we have one GPS measurement. So here you see longitude, latitude, and altitude information. So from this log file, in this post-processing, we only use the timestamp here and the position. And then what we see here is this, when we process it, we will have GPS X, GPS Y, and GPS Z. And if you look at here, there are 167 points in those variables. So that means, so this experiment took around 167 seconds. But when you process the measurements, you see we have the measurements such as AERPAW 1. If you look at here, it has 8,213 points in the measured data. So therefore, we have more measurements than GPS positions. So, but the first thing that we do after we process the log files is check the quality, and if equality is above the threshold, we keep the measurement, otherwise we discard the measurement. And the default threshold value is 70. After this is done, here we go through all the measurements, and then we find the location of the measurement by using interpolation of the locations found by the GPS. So as I mentioned, GPS is measured every 1 second, but we have more measurements than the GPS positions. So therefore, so these two plots, you'll see GPS points are much less than the measurement points, but they all correspond to the same experiment. So you see, like if you plot the altitude based on the measurement point versus based on the GPS points, you have the same trajectory. Once we have these figures plotted, so you can also generate files from the plots by running this plot. So this plot is disabled by default, but you can right click and then evaluate selection. So you see it will create a figures folder in here, and then these plots will be saved as in the PNG format. If I run this, you see figures folder is generated, and then the files are created under the folder. So the last thing that I would like to mention is to generate KML from the experiment. And then what does it do? If you see here, so when you generate KML, you can use Google Earth to plot the measurement, and then you can see it on Google Earth. So how do we do that? We do it by using this input.csv file, which our main script creates. And then we have this Python code, which is called KML generator. So in order to do that, you go to the command prompt or a terminal, and then you go to the folder that that your code is, and then you type this code. So I copy it and then paste it. So this will, so if I check, if I open the so if I open this input.csv, you'll see what it contains is it contains the measurement point. There is a timestamp. It has the position, the longitude, latitude, and altitude, and there is the measurement. So in this case, the measurement is the received signal power. So by the way, this power is in relative and is in dB, so it's not absolute power. So you see it starts with 43 and then goes down and then goes up. So this also takes some time. So I think there are, after we discard the measurements that has low quality, so we have around 5,000 measurements out of 8,000 measurements. So once this finished executing, it will generate this out KML file. So it actually started writing on it, and then we can use Google Earth to open this file, and you can download it in here. So download AERPAW on desktop, and then in the manual, I think there is a link to Google Earth. If you don't have it installed, you can download and install. So now is execution is finished, and if we check the folder, you see the out.kml is generated. So I double click on it, and then it will launch in Google Earth. Yeah, you can zoom in, and so this is the how it shows in Google Earth. So I'll close this. So the last thing I will mention is, like, when you copy the files, if you're not using Mobile Xterm, and if you're using Ubuntu or macOS, you can use SCP to copy file from the terminal from your virtual machine into your local computer. So in that case, you will have a terminal like this. So let me go to so my C folder, users, .ssh, where my SSH key is. So here you see my SSH key is in here. So then I can use this SCP command, which is similar to SSH, but for copying files. And then you provide your private name or private key, and then root at the IP address. So let's say we would like to copy results folder. Then you can do like this, and then you copy it under your username, like this. Okay, so you do it like this. Okay, sorry. So I think I need to be. So I need to be here. Okay, I think in this case, -1. Okay. So maybe it's minus little one. Yeah. So this is how you can. So if you can go back to the folder that you downloaded. See here, there should be like results folder. So all the log files. So this is another way to copy the files from your experiment into your local computer. Thank you, and I hope you have a nice workshop.